Well, it is a great pleasure to introduce a friend of IMSA. He was already here for our Super Bowl conference right before the pandemic. Too bad he's not here this one time. But again, visa issues again. But it's a great pleasure to have a friend of IMSA. Carlos Alfonso Ruiz is one of the most influential young mathematicians in Mexico at the moment. He graduated from the University of Oxford, studying the field of logic in the Khrushchevsky. Then he came back from Mexico and founded the Bourbaki Institute, where education and research in pure and applied mathematics is performed. It's a private institution, and he's the director of the Bourbaki. He's well known for his contributions both in the field of logic and data science and artificial intelligence. And it is a pleasure to have him today here at IMSA, teaching a mini course. This conference is research talk, but then there has been two mini courses, the one on quantum geometry, and now this mini course. And this first lecture is about quantifier elimination. Carlos, thank you very much for being here with us.
Thanks a lot, Ernesto. I'm very happy. I can't say I'm very happy being here, but I'm very happy to share this time with you. Can you hear me correctly?
Yes.
Yeah. Okay. Yeah. I'm honored to be here. I'm honored in general to have any opportunity to talk about math with Ernesto and with all of you. So today I will talk about quantifier elimination. Especially I will give some examples of how you could use quantifier elimination to prove, or perhaps I should say, to understand the geometry of fields, and I'm talking about fields in general. They could be p-adic fields. It could be also about algebraically closed fields, and in general, I will leave this open to determining about which fields we're talking about, right? So this mini course, I could give you a quick overview of what I will talk about. So first of all, I will say something about definable sets. Definable sets is a concept that comes from mathematical logic. And just to say in a few words, a set is definable if there exists a first order formula in some language such that the points or the elements that satisfy this first order formula is this set, right? So of course, this definition depends on the language that you're using. I will talk about the language of rings. And in the language of rings, of course, you could define a polynomial, you could define an equation, or the zeros of a polynomial. But in general, this notion of being definable is larger than just being a Zariski closed set or something like this. In fact, the way I will present this is you could choose any or almost any set of atomic definable sets, and then you could enlarge this family of atomic definable sets into a well-known category of definable sets, and the geometric and combinatorial properties of this family is very important. In particular, it's something that is very important and useful in the motivic integration theory developed by Reshkovsky and Kazhdan. Yeah. And this is what I will talk about in my second in my second talk. So this is point 5. I will tell you what the second and third and fourth points are, but here I could talk about valued fields. So this will be the beginning of my next talk. Of course, I will talk about algebraically closed valued fields, but the goal of this mini course is to arrive to what it's called Reshkovsky Kazhdan motivic integration, right? So the main goal is to give you a fairly complete exposition of what definable sets are in the context of Reshkovsky and Kazhdan. And I hope I will have enough time to show you how this understanding, how a full understanding of what definable sets are in this theory could have applications in geometry, in birational geometry, for example. Okay, so our main goal is to talk about definable sets in various contexts, and the context which is more important and which is interesting for Ernesto is this category of definable sets in an algebraically closed valued field. Okay, so this will be on Saturday. Okay, and I continue with my exposition. I will talk about quantifier elimination. So I will give you a precise statement of what quantifier elimination means. I will briefly talk about something that is called elimination of imaginaries. So this is elimination. Well, and then just to make this talk less logic side, I will give a brief description of how both quantifier elimination and elimination of imaginaries could be used to prove something that is called Veil-Chunk theorem. I don't know if you know this theorem, but this is a well-known theorem by Veil, which tells you that I mean the weak version of this theorem tells you that if you have a constructible set inside an algebraically closed field, this this constructible set is also a group. You have a group law, then immediately this set, or this definable set, constructible in the language of algebraically closed fields, is an algebraic group, right? So of course this is not immediate, because in the definition of being an algebraic group, you need the set to be an algebraic variety, and in principle, a constructible set won't be an algebraic variety, because a constructible set by definition is just a Boolean combination of Zariski closed sets. Okay, so this is a weak version. I will talk about a slightly stronger version, which I believe is very interesting. And this theorem uses both quantifier elimination and elimination of imaginaries. And so I hope that after this talk, you will find both quantifier elimination and elimination of imaginaries an important property. Okay, good. So I think that I cannot hear you pretty well, but I can see you. So if you have any question, you could just raise your hand, and I will I will understand that you have a question, right? Okay, good. So first of all, I will talk about definable.
Can you hear us? Can you hear what we say?
Now, yes, yeah.
Okay, so we're okay. We're okay.
Yeah. But this was just a test, right? You don't have a question. No. Okay. So I will talk about definable sets. My first definition, won't use anything about the logic, about the first order formulas. I will just give a definition that would be very geometrical, or I hope it will be very geometric flavor. Okay, so imagine you have any set. Of course, we are interested in the case where M is the complex numbers, the p-adic numbers, or the p-adic field, but you could also think about the real field. I mean, for me, M will be any field, depending on which theory I'm talking about. So, for instance, you could think of these as the complex numbers, right? So the set of atomic definable sets is any family. I will say any family of subsets D inside the nth Cartesian product of my field. Okay, so any family of sets of subsets D inside an arbitrary Cartesian product could be an atomic definable set, provided the diagonal inside the Cartesian plane is contained in this family of D, right? So this is.
So I just fix a family, or I just fix a family to begin with, or?
Sorry.
So I just fix a family to begin with. Or?
Exactly. Yeah. For example, you could say all Zariski closed sets inside any affine space, right? Yeah. You could also say, for example, all semi-algebraic sets inside a real closed field, all closed subsets inside a valued topology, evaluation topology. Yeah. Okay. So this is the atomic. Those are the atomic definable sets, and then the definable subsets of M is the smallest family. So the definable sets.
With respect to the atomic family, with respect.
Of course, yeah. So the definable sets with respect to the atomic definable sets is the smallest family, such that the smallest family, of course, again, I'm talking about a subset in any Cartesian product, such that the following conditions are satisfied. Okay, so first of all, as Ernesto pointed out, at any atomic, all atomic definable sets are definable. Yeah. Then I will close this under finite Boolean combination of definable sets, right? So if I take A and B, which are, I will start saying the definable sets inside M. Okay, so definable sets in the structure M. Of course, A intersected with B will be again a definable set. A union B will be a definable set. And the complement of A will also be a definable set. It's very important that we are talking about only finite operations, right? So, for example, yeah, for example, I cannot take an infinite union or an infinite intersection of definable sets. This is not allowed. This is a very important, restrictive, but essential part of model theory and of this logical approach to geometry or whatever, however you want to. Okay, good. So this is the second. I mean, this is if you think about formulas, first order formulas, of course, those properties are immediate, right? Because you have the conjunction, you have the disjunction, exactly, and you have the negation of your formula. Yep. Okay. And then this is a very important property. Suppose that you have some definable set living in m plus n plus m dimensions, sorry. And suppose that you have pi, a projection from this space to, for instance, this space, right? So this projection, I mean, just the coordinate-wise projection into the last m coordinates, okay? So pi is just the standard projection. Then this category or this family of definable sets should be closed under the image of this.
So this is the for all quantifier for n parameters, or?
Yeah, for any n and for any m. That's true.
But this is like a for all quantifier for the first n parameters.
Oh, I see. This is like an existential quantifier, right? Right, because something is here, so an element will be here. Do you agree if there exists some, let's say, v inside mn, which satisfies this this formula, this first order formula, right? So this projection is exactly the
M exists.
There exists. Yeah. I want to talk about the for all quantifier because we have this. So I could stop here, right?
Yeah.
Is it good? Okay. So which examples do I have in mind when I talk about definable sets? For example, some examples of atomic definable sets are.
This is the definition of the definable given the atomic family. And we are going to see how to eliminate the quantifiers.
Right, right. So
quantifier elimination, Alfonso, is not a theorem, is it? Because you're projecting and you're eliminating quantifiers.
Sorry, I cannot hear
you. What is the mic?
No,
that you are already in the definition of definable. You didn't have any existential. Now you're showing a result. What is exactly that the projection is a definable? That's a theorem or that's a part of the definition?
It's part of the definition.
But I thought this was a result.
No, because then quantifier elimination tells you that given a formula with an existential quantifier, you could replace this formula with a formula that has no existential quantifiers. So quantifier elimination tells you that the formula that we're using to define this could be replaced with a formula without quantifier. Of course, the obvious definition of this set includes an existential quantifier, as Ernesto pointed out.
But just to get ahead of the game, just to get a little bit, to get in the right mood, for this, the evaluation and the real numbers eventually, or the order will be important to do this kind of discriminant theory to eliminate the quantifier. Is it so? this is based some more part.
Yeah. That's a good example of a formula that could be could eliminate an existential quantifier. I mean, there is also a straightforward example. So say that you have a formula if phi A, B, C, right? So the definition of this formula is there exists an X and there exists a Y, such that A times X squared plus BX plus C is equal to 0. And at the same time, A Y squared plus B Y plus C is equal to 0, right? So this formula has a quantifier, of course. But this formula could be replaced with an equivalent formula that has no quantifier, right?
The discriminant.
Just the discriminant, right? Yeah, so I could just say that A is different from 0, and then I could say that B minus 4AC it's larger than 0. Right? So I could also, for example, say in a first order language using quantifier, that matrix is invertible, right? So I could say there exists an alpha, beta, gamma, and delta, such that this is equal to the identity matrix. Do you agree that so the fact that this matrix is invertible, it's you could write this in a first order language, right?
That's right. Yeah.
Yeah. So we know that this formula is equivalent to the determinant of the matrix being non-zero, and of course, this formula has no quantifiers, right?
Well, it tends to be this kind of discriminant formula.
Yeah. So the classical proofs or the first proofs of quantifier elimination, they in general use these discriminant techniques. Okay, but I mean it's important to say that those so quantifier elimination could have a very geometrical proof. So for instance, the proof by Chevalier. So quantifier elimination in the geometric sense, it's called Chevalier theorem, or one of Chevalier theorems, right? That tells you that if you have an algebraic variety or two algebraic varieties and you have an algebraic morphism between those algebraic varieties, and you have some V constructible set inside V, then the image is constructible, right? So there is a very nice proof of this result, a geometric proof that has that mentions nothing about discriminants.
There is on the spirit, already this Chevalier theorem is on the spirit of this cell decomposition.
Right, yeah. So, I mean, this cell decomposition is used to prove, or could be used to prove quantifier elimination when you take as your atomic sets, you take, so here our atomic sets are Sariski closed, of course. And if you consider semi-algebraic sets, so when I say semi-algebraic, I think the points in Rn such that there exists some algebraic polynomial P and some other algebraic polynomial Q, which satisfy an equation like this. So that's what I mean by a semi-algebraic set. Okay. So the category of definable sets, when I consider semi-algebraic, has a very important property, very close to quantifier elimination, though is not exactly quantifier elimination. And this, in the context of semi-algebraic sets, it's called Tarski-Seidenberg. Okay. One of the main goals of Saturday's talk will be to define precisely what do we mean by definable sets. Sets inside an algebraic closed valued fields, right? So it's a bit more complicated in this scenario, because instead of having M, a single set, we will have M, we will have gamma, and we will have a small k, three different sorts, right? So you could also talk about a structure with its atomic sets and its definable sets that has different universe. This is what it's called multi-sorted model theory, right? Okay, so the idea of Saturday's talk, of course, is to tell you precisely what do we mean by definable sets inside algebraic closed valued fields, and to explain you why quantifier elimination in this theory of algebraic closed valued fields, it's important from a Grothendieck ring point of view. So I will define the Grothendieck ring associated to a family, to the family of definable sets, and this ring is well understood. Is well understood by Reshkovsky and Kashdan, right?
Yeah.
I might say
part of the problem is that this tree-like structure in the order, or what's part of the problem is that the order is no longer linear but tree-like structure.
I mean, this gamma is the value group, right? And this value group might not have a total order. It's true in principle. This is the residue field, and well, I wouldn't say that the main problem is the order here. I think that the main problem are the quantifiers. So quantifier elimination do tell us something about the geometry of definable sets. So quantifiers here are difficult because I could use, for example, I could talk about definable sets inside the value group that use a quantifier over M, right? So this is still a first order formula. I just need to restrict where my variables live, and that's good. Okay, so this will be the main difficulty. Although Reshkovsky and Kashdan, they define a very intelligent structure that you could get rid of this multi-sorted language. But I will explain this on Saturday.
Yes.
Good. Okay. I think that I missed my definable sets. Okay. So just some notation that you might use, you might see in this short course. Sometimes I will say that M satisfies the formula phi of A. So this is a first order formula, and what I mean is just that A is an element inside the definable set associated to phi. Yeah, sorry. So this notation, that's what I mean. That's what I mean by this notation. Okay. Good. So as I mentioned, quantifier elimination has a deep geometric flavor, but it's also a very robust notion. Let me give you an example of a corollary of quantifier elimination in the case of algebraically closed fields, right? So this statement could be obvious, but it's could look obvious, but it's perhaps the easiest way to prove it is through quantifier elimination. So suppose, for example, that you have F subfields of F prime, and let's say that they both are algebraically closed, right? And let me think of S as some finite set of polynomial equations. But I'm also talking about inequations. I don't know if I'm speaking correctly. By inequations, I don't mean inequalities, of course. If for example D is a Zariski closed set, then I'm talking about the complement, so the open Zariski closed or open Zariski sets. Okay. So a consequence of quantifier elimination is that if S is over the small field, okay, and S has a solution in F prime in the larger in the larger field, then quantifier elimination immediately implies that S has a solution already in F prime. Okay.
Nice.
Yeah. So this is what we call in model theory model completeness. So model completeness is a weak version of quantifier elimination. If you have a theory, for example, the theory of algebraic closed fields, which eliminates quantifiers, then immediately this theory is model complete. I don't know if you agree with me, but this is a naive version of null Stellensatz, right? So actually, there is a proof of null Stellensatz that of classical null Stellensatz that uses this quantifier elimination result. Okay, and something that it's very.
Let me ask to elaborate a little bit on the relation to null Stellensatz.
On the relation with the null Stellensatz? Yeah, of course. So so I will talk about a very weak version of null Stellensatz theorem, right? So I'm not saying that the general version of null Stellensatz. Actually, I've always wondered if the most general version could be proved just using quantifier elimination. Just let me state correctly the version.
Using a projection, so maybe.
Sorry?
I mean, the classical proof is Shafarevich or whatever uses these projections, maybe.
Yeah, so I mean, I will talk about this version. So say F, it's an algebraically closed field, okay? And suppose that P is some prime ideal, some prime polynomial ideal here. Then, yeah, I think that's all we need. Then this set of elements that satisfy P, sorry, so the set of elements inside F that satisfy P is non-empty. If you want, maybe not now, but on Saturday, I could give you a full proof of why quantifier elimination implies this version of null Stellensatz. Yep. Okay, and what is interesting is that the quantifier elimination over algebraically closed algebraically closed valued fields also gives you a statement of this kind for algebraic closed-valued fields, where, of course, I should say what do I mean by the ideal but by which ideal I'm talking about. But remember that we have definable sets coming from the value group. Okay, so not all definable sets are algebraic in this other setting. So a precise statement of what null Schelling sets means in the algebraic value field should be clarified. Yeah. So in the first 10 minutes of Saturday, I could give you a full proof of this self-contained, if you want.
Thank you. Thank you.
Okay, good. So where else? Yeah. So I also want to show you some examples of the bad scenario, which is an scenario where you can't eliminate quantifiers. So perhaps the most famous one is this formula. So we will talk about our exp, which means that my definable sets are the semi-algebraic sets, okay, plus any set inside the real numbers or Cartesian products that use the exponential function. So I'm allowed to use exponential function and not just the sum or the product as in the theory of rings, and also, of course, the order for having semi-algebraic.
Just a quick question. The fact that we add exponential function also adds or not the logarithmic function?
Not all times. Okay. Yeah. I mean, actually there are some examples.
One really has to write it in terms of exponentials.
Exactly. That's the only extra atomic set that I am considering. So when I say atomic set, of course, I mean the graph of the exponential function in R squared. Yeah. Okay. So this is an example given by Osgood, and the formula it's something like this. So y should be larger than 0, and there exists a w such that wy is equal to x, and at the same time y exponential w. So this formula was shown by Osgood.
What is the last part? Y what? Y equals?
Y times the exponential w.
And y times exponential w not equal nothing. That expression, I don't understand the expression.
Oh, sorry. There is an equality here. And at the same time, y equal to e w.
Okay.
Okay.
Can you recognize this a little bit as a log transform or?
Sorry.
Well, sorry.
This could take a bit longer, but if I have some extra 5 minutes on Saturday, I could give you a hint of why this is not definable. But it's not.
So the statement is that this is not definable.
This is definable, of course, because I am showing you the.
But not quantifiable. You cannot eliminate x. You cannot.
Yeah, exactly. This is not equivalent to a quantifier-free formula. as, for example, this formula was equivalent to a quantifier-free formula.
Because a typical logarithm would neither exist, but would not be coupled with the same variable above and below the multiplication. So the problem is that
yeah, it's very, very close to these arguments. So if you want, I could also give you the reference of a short paper by Van de Dries, where they give a list of maybe 10 different first order definable sets, which are not quantifier free in the field of real closed fields. In the theory of real closed fields. Okay. Good.
Well, why we need is wy is equal to x. Excuse me. So in your previous page.
Here?
I mean, why we need wy is equal to x.
to make it complicated and not have quantifier elimination.
Yeah, exactly.
But it's not quite log transform, isn't it? It's not quite log transform.
Yeah, but y equal e to the w is no. Yeah, I mean, I can't understand why. So it's
to make it complicated and not be able to eliminate the quantifier.
okay. Thank you.
Let me think about a short argument of this.
Yeah.
Okay. Good. So the next thing that it's important if we talk about quantifier elimination. I have some other examples, but perhaps I don't have enough time. For the other example applications. Okay, so the other result, which is very important in the in this theory by Reshkovsky and Kazan, is the elimination of imaginaries. Okay, so a theory eliminates imaginaries if all definable equivalence relations are witnessed by a definable function. Let me explain what do I mean by this. So suppose that you have E, some definable equivalence relation. So this means there exists a formula which defines this binary relation. Okay, so we say that a theory eliminates imaginaries if for any definable equivalence relation, there is some definable function, right, such that this equivalence relation is satisfied for x and y, if and only if x is equal to f of y. Okay. So, I mean, a good way to think about this. So you have M or some Cartesian product of M, and then you quotient this by E. Okay. So you have some map, right? That goes from Mn into this quotient, and so the statement is that if this function is definable, if you could find a first order formula that defines this function f, Okay, then this theory eliminates imaginaries. Okay, so
what do they mean by imaginaries? What are we imagining?
Yeah, it's a horrible name. I agree, because, for example, complex numbers, they eliminate imaginaries, right? You have elimination of imaginaries for algebraically closed fields. In particular, you have elimination of imaginaries for complex numbers. Okay, so this comes from some historical problem in model theory. Someone decided to call those elements imaginary elements because they are not part of the traditional structure, and if you don't need to enlarge your original set, then you eliminate imagine.
I can't imagine why this is called like this. Well,
Yeah.
But it's nice to demystify the meaning of this expression. I read it so many times, and I was trying to imagine the imaginary.
Yeah. So in particular, elimination of imaginaries in algebraic closed fields, it's something very easy. It's also something related to discriminants. But elimination of imaginaries for algebraically closed valued fields, it's perhaps one of the deepest results in model theory of valued fields. It's very difficult. It's one book proof the elimination of imaginaries of algebraically closed valued fields. Okay. This is used in the theory of motivic integration by Kazan and Ruzhkovsky, but in a very subtle way. I will explain you why this is important. But I mean, I would like to present both elimination of imaginaries and elimination of quantifiers as the model theoretic tools in the motivic integration theory. Okay, so if you have those results, then you could understand this Grothendieck ring. Good. Algebraic closed fields eliminate imaginaries. For example, this theory has elimination of almost elimination of imaginaries. You need to add something. But maybe, well, I don't know if any of you have any question.
So just what you said, this Rx has elimination of imaginaries, or
this, so if you add,
we're super interested in Rx.
So if you add also partial analytic functions, by partial functions I mean just the graph of an analytic function around 0. If you add this to the language, if you add this as atomic sets, then this has elimination of imaginaries.
Fantastic.
Yeah. And this result is perhaps as difficult as it is for algebraically closed fields. It's just a discriminant-like technique. Okay, good. So because I don't have a lot of time, I will talk about the axe quotient theorem, which is a result, which is also a consequence of quantifier elimination in the context of algebraically closed valued fields, right? So this theorem, at least from a model theoretic point of view, tells you the following thing. So suppose that you have phi, any formula or any sentence by let's say any formula, okay, and this formula is allowed to have to be an algebraic formula, meaning that it involves the language of rings. So it's almost a polynomial, but it could also has something to do with the valuation of some valued field, right? So here I am using some valuation in my language, and this result tells you that this formula is true in FP, so the finite field of characteristic P. At least it's true in a cofinite number of primes. Okay, if and only if, so it's true here, if and only if this is also true. Sorry, here. Yeah. So in fact, as I will say it, I should say the power series over the finite field. So this is true if and only if it's also true for the p-adic numbers. So it's also true for QP, and again you need to say this at least in a cofinite number of primes. Okay, so this is what model theorists will call the Axe quotient theorem. And do you agree that this is also a consequence of quantifier elimination?
I know the proof. I don't think the other guys.
Perhaps it is less obvious. So the proof of this result uses some ultra products. So the idea is to define the ultra product of those fields. So overall primes, you consider a quotient of the direct product of those fields. You also do exactly the same thing over all prime numbers. You quotient this by an equivalence relation. So it's a filter, and you could prove that this ultra product is a field. It satisfies the same theory of algebraically closed valued fields, or I mean, the algebraic closure of these satisfies the theory of algebraically closed valued fields in characteristic 0, and because those two fields satisfy this theory, then essentially the same argument we have here works with the quantifier elimination technique. Okay, so actually this Axe quotient was first proof using model theory through this argument.
Very nice.
Good. Okay, so maybe it's good if I stop here and I can take okay.
So are there any questions for Carlos from the audience here or from Zoom?
So maybe I,
Yeah, John?
yeah, can I ask you one question? So in your proof of this X theorem,
Yeah.
you assume that there is an argument which such that this formula satisfies something like that. So, but how can you guarantee there is an argument?
That there is an
argument. So I mean, in your proof of this X cosine theorem, I think you assume there's your proof assume there's a kind of argument which is varied in for some finite field, isn't it? So how can you?
So in this In this theorem of exclusion, I am assuming that you have a predicate for the evaluation. This is very important. Because if you don't have a predicate for the evaluation, then you won't eliminate the quantifiers. I don't know if that's...
So that's all you need, right? So you don't...
Yeah, that's all you need.
Okay.
And this predicate for the evaluation, this comes from this theory of C-minimality, or where does it come from?
So this predicate is the function that goes from the valued field into the evaluation group. Yeah. So this is how you relate those two sorts or the two universes through this evaluation.
Okay, this is very, very nice. We'll look forward for the continuation of these mini curves. And well, let's thank Carlos again. And we'll continue tomorrow. Thank you very much.
Thank you very much. Bye.